Thanks everybody for bearing with us today. We got a very fantastic panel. We have the pleasure of joining us today as the Director of Research at LeafLabs, Jeff Ciesielski. All right. And then Justin Schneck, co-founder and Chief Product Officer at Peridio. And today we're here to talk about some pretty cool work that's happening. It's a fun panel because Jeff works on the tiniest of edge or like the most surgical of edge. And then I think like what we do often at Peridio is very resource constrained, but Jeff is carrying the torch into a much further tiny direction. And Justin has a lot of experience on the embedded Linux side and customizing and building Yocto distributions. So really excited to get into it. And we're going to talk today about scaling AI at the edge and engineering truly next generation embedded systems. Yeah, a little intro. I'm Bill, CEO of Peridio. We do firmware management for embedded companies. Justin, why don't you introduce yourself? A little more interesting background.
Hi, yeah, head of product here, co-founder of Peridio, and yeah, just tons of experience in building, shipping, maintaining embedded Linux in that domain. Also, a co-creator of the Nerves project, and here today to be able to talk about more of the micro tiny edge. Looking forward to this conversation with Jeff. Yeah.
LeafLabs, what do you guys do?
A little bit of everything. Yeah. So my name is Jeff Ciesielski. I'm the director of research here at LeafLabs and also senior technical staff. So LeafLabs, we apply our trade in what we like to call digital frontier, right? So this is like where software meets hardware. So we work a lot in like heterogeneous compute systems. So FPGAs plus a microcontroller plus microprocessors. We also do a fair bit of electrical engineering. So we work sort of kind of from that, like digital design, ASIC creation, all the way up through sort of like what I would say middleware. So we do some embedded Linux, Yocto, things like that, and then spend a lot of our time though in sort of like deep embedded, elbows deep in pointers and C, and then writing a lot of like Verilog and other HDLs.
Awesome. And then what is like Leaf's like primary, like if somebody's wanting to work with Leaf Labs, what would bring them to that conversation?
Yeah, so at Leaf, we have a pretty diverse array of clients. So I think where we see people coming in is when they're working on like really hard research projects and maybe they don't have deep embedded knowledge on their team, so they come to us because we're able to. We pride ourselves on being able to sort of parachute into kind of any environment, whether that's you're starting from scratch, you've got 5 million lines of code and sort of anything in between, and being able to absorb what you're doing kind of independent of the domain that you're working in and really surgically help you, get in there and help you sort of surgically fix your problems or add functionality that you maybe, we're seeking to add and just didn't have on staff. And so, we work with Fortune 100s. We work with, it used to be FANG. I call them Mangoes now. They're research labs. And then, but what we really love doing, is working with small companies, small labs, working on sort of like crazy science experiments, especially in like the applied sciences, biology, neuroscience, things like that. That's really where we sort of have carved a niche for ourselves.
And how large is your team?
Right now, we're about 20 people, mostly engineers. So we run pretty light and we try to keep it small. I mean, I think that like one of the magical things about LeafLabs is that we're all on a first name basis. We're all very, sort of close and friendly. And so that lets us kind of work very fluidly as a team, right? Because like sometimes you get, you need one engineer, you need 5 engineers. Like when people hire us, like they're not hiring, like we're not like a staff augmentation service. Like you hire LeafLabs. So if it takes 5 of our engineers, sort of combined brain power, we bring whatever we need to bear to solve your problems.
Cool. For those of you who don't know, Peridio, we're a platform for software distribution, management of next generation devices. And our teams and companies focused on helping customers take like robust and secure products to market in a physical space. So embedded solutions, embedded Linux, embedded software management, cohort-based distribution workflows, release phasing, centralized source of truth for operations teams, and all the fun stuff. And so if you're excited to talk about firmware management, device management, or getting Yocto online and rolling, please reach out to me after the call. So today, again, fantastic webinar. Super excited about the conversation we have ahead of us. And we have really 3 topic categories we're going to get into. At the highest level, delivering really next generation AI applications at the edge, and very interesting panel today, as we said earlier, about Jeff's experience versus Justin's experience, and really what everybody is seeing in these next, like this next wave of products that are now possible. So we're going to talk about when less is more, like when to microcontroller, when to FPGA, maybe even when to microprocessor, and then also some of the physical safety ramifications of edge and AI. A lot of what we hear in AI safety is around general like these like autonomous systems, maybe like purely digital and LLM perspective. And I think that this panel has a very unique perspective on what this means in hardware too. So maybe like robots walking around or drones knocking on your door. Hopefully not. Getting into it at the highest level, I'd like to just kind of open it up and talk about designing under constraints. And we had some really nice conversations yesterday about less being more. And I'm curious, either of you who wants to jump in, and like when do the constraints actually force better or more interesting solutions?
I know Jeff lives under these all the time, but yeah, I think constraints really do force you into having to identify things that you'd never maybe even consider before. The couple quotes reach creativity is the art of living within constraints. I mean, there's so many different ones about art being born from constraints in general. And ultimately, it's this interesting place where it's this paradoxical idea that limitations somehow will like spark the innovation and creative problem solving, and to find novel solutions that without constraints, living in an unlimited area, you'd not really have yourself challenged to be able to find. So under that guidance, Jeff, yeah, I want to hear like where that really colored your world and making that art shine.
Yeah, well, I mean, I think engineering sort of is is the science of constraints, right? I mean, like, look, anybody can like dam a river with rocks and drive over it, right? But like, it takes an engineer to make a bridge that barely stands, right? I think that you know, I think it's really easy, especially in today's world in embedded systems. You can buy outrageously powerful microcontrollers. A Raspberry Pi 5 is like 10 years ago that would have been like a not terrible desktop computer. Like just like by the numbers, right? And I think that when you start looking at like what it takes to really deploy hardware and scale out a hardware business, you can't just always buy the $50 module and slap it into your product, like either just due to resource like actual availability constraints, right? Or because swap, size, weight, and power, like you have to start thinking about like how to scale that down. And so when you start to really look at okay, well, like what makes sense to really deploy, and especially like in your guys' space, right? When you're for me, look, I build one-offs, right? Like I'll put the $500 processor in there, I don't care. But when you try to scale to 1,000 units, 10,000 units, 100,000 units out in the field, 50 cents on a part actually really starts to hurt, right? And so I think that and what that translates to directly is resource availability, often in like a microprocessor or a microcontroller. So going with something that has half as much SRAM might save you 20, 30 cents on a bill of materials, but then scaled out to production, like that actually starts to really, that has a real impact on your business's bottom line. So I think that like it's really important when you're, as a product development group, or as an R&D group, like when you're thinking like, okay, we have aspirations of scaling something out, understanding that scale, like you can draw a direct line to like dollars, like even with like volume, breaks on parts, it really starts to hurt. So if you design for a system that is kind of, if you have a range of parts and you design for the part at the top, and you just assume that's what you're going to have, like you never have any room to like claw back any of that cost, right? So like something I always tell clients is, pick a product family. Like if you're trying to design, just thinking about constraints, pick a product family and like try to design for something in the middle of that range, right? That gives you, so you can always pay money to solve the problem for you later if you don't have enough, but it's a lot harder engineering time wise to like claw back those resources later. I mean, I've definitely worked on products before where literally counting bytes, like we've got 5 bytes, you want to add a feature, you got to find every byte of that feature to get it in the firmware, and it's an awful way to live. Nobody
That's
I'm curious, like
there's
the
an interesting crossover there. Like you mentioned that you know with a lot of the one-offs that you're making, like not being constrained necessarily by the bill of materials cost. But there has to be some consideration, at least with the breadth of clientele that you have, that you work with, to where you know that there's potential for that not to just be a one-off, and that it would want to scale. You know, and so like coming in from the start, like I guess like you're saying is start shoot in the middle, so that maybe at least you have some footing in either direction if you had to.
Right.
Yeah, I was just curious in that case, like you know, it also made me think about situations where have you had the need to react to the bill of materials, to where you know you want to shoot in the middle, and that maybe in a situation where in order to be able to solve a problem and get the measurements that you want, you could spend you know tons of money to do so. But if you shot in the middle, you could get your hands on these types of sensors, and that in that scenario, using machine learning to be able to do some sensor fusion would help you derive a result in a constraint. So it's like introduction of AI and machine learning can help you deal with the constraint. Is that have you had that?
So not directly. I mean, like I think that, one of the things with throwing AI and ML at a problem is that you instantaneously increase your compute requirement, right? So a lot of times, doing AI, like throwing a machine learning model at a problem that could be, especially with like sensor fusion. Like sensor fusion is a pretty well understood problem, right? If like use like a Kalman filter, right, and you sort of, like, depending on what you're doing, right, like that's a pretty well understood analytical problem. But when you start to say like, okay, like let's increase the, let's try to use software to correct a hardware problem. A lot of times what ends up happening is, your NRE goes through the roof. And that's an
Mhm.
important consideration, right? It's like you have to sort of balance. I mean, that's always the difficult part of a hardware group, right? Is like you have to balance bill of materials with NRE difficulty in bringing something to product, right? Like that's, oftentimes like why, we really like ST parts at LeafLabs. We've been using ST parts for well over a decade. And it's because like we understand them, that they have like a huge breadth in the industry, like in terms of like where all their different product lines sit. Um, but we understand them well, and so our NRE costs are low because we don't really have to spin up on them every time, right? Whereas like maybe a TI microcontroller would have like way better peripherals for motor control, but it's going to take us 3 months to actually fully understand the thing, right? So,
Mhm.
so I think that like speaking, but getting back to your question about AI, like when we try to deploy AI, we try to do it very sparingly, and in situations where AI shines, right? Like it's not in these like sort of well understood mathematical models. It's where you have sort of this like crazy high dimensionality in a function that you're trying to fit to, right? So like object detection, object sort of differentiation, right? Where it's like really maybe like traditional computer vision starts to break down. And so we try to identify those spaces where the NRE is worth it. And
Mhm.
also because, AI edge cases are, numerous and belligerent. And so you have to, really chase them down. And so it can sort of increase your costs a lot, like over the long term.
I think this is an interesting point too around just like we talked about like BOM constraints and hardware constraints, and there's like also AI is challenging because everybody is like kind of painting with their imagination right now, and like problems used to be discrete and people think that now you can just throw an AI at it and it's now possible. So how do you like work with your customers around the limitations of AI and like less about the hardware, but really what is physically possible or design wise possible with like the time and resources that you have?
Yeah, that's a really good question. So I think that, what we try to when we there are a couple of different dimensions that we sort of judge where AI might be a good fit for some of our clients, right? One is, where are you really trying to deploy, and are there models that are actually capable of being deployed in that slot, sort of, or in that socket, as some might say, uh, you know, under those constraints. So, you want to do object detection, like sophisticated object detection, or like multi-object tracking or something like that. Like you're not going to do that on a microcontroller, right? The models are too big, they require too much memory bandwidth, they require, too much processing power to act, and you want to do it like on a microcontroller with a battery, right? It's just not going to work. um Correspondingly, maybe maybe there are other types of machine learning. Because like we also like people think about AI and machine learning right now, like LLMs are currently the hot thing, right? Like a couple of years ago, it was like GANs. Now it's, but like there are other types of like what might call like machine learning, right? Where it's doing like I can't remember the name of the algorithm, but basically like trying to do like voice detection or like spoken word detection. There are algorithms for basically like automatically stretching and auto correlating sound waves, and like they're sort of machine learning kind of adjacent, right? And where you might try to do like an RNN to do the same thing, right? But it might give you weird results. It might be very, very difficult to deploy, whereas this other model is like sort of very well understood, right? So it's really like trying to understand, work with our clients and ask the why, like why do you want to do this? Why do you think that you need this particular type of machine learning? Why do you think that machine learning is the right answer? And trying to help them fit, sort of with their constraints, with whether that's cost, whether that's overall cost of ownership of their system, or if it's like resource constraints.
Hmm.
Yeah, it's a difficult thing because like we work, a lot of the AI ML work that we're doing right now is actually not even in deploying models; it's in accelerating those models, right? So like building custom accelerators, and clients are shocked at like sort of the cost of developing some of these systems, right? Because it's like you want to run llama, a 90 billion parameter llama model, that's 450 gigabytes per second of memory bandwidth that you have to contend with, right? Like
Yeah.
you're not doing that
Not
on a
happening on
microcontroller.
your
Yeah.
Raspberry Pi anytime soon.
You're right, yeah.
That's it's really interesting. I think some of the best product designs, like we're talking about constraints in engineering and having to deal within those, and how that kind of breeds really novel and delightful artistic solutions, under them. But when introducing AI and machine learning into the mix, it kind of seems to me like that's an introduction of an unconstrained system. Like a lot of these have edge cases that you can't really define very easily. Like we're in a phase of AI and ML, where there's a famous curve that you can imagine as a meme, of what phase we might be in, because we're certainly starting to find out that it's difficult to be able to reason about all the different ways that this could end up yielding results. And so it's a very deliberate choice to be able to introduce, for the sake of argument, an unconstrained portion to your constraint system. I think the best products are ones that most clearly define and can interrupt with the boundaries in which they've been designed to be able to adhere to. And we kind of take a little bit of this for granted, I think, in embedded systems, because so oftentimes in a traditional software development, you certainly have control or knowledge over the environment you're deploying into, but oftentimes in embedded systems, that's a little less that you can gravitate to. This might get thrown into the wild. It might be raining. It might have a hailstorm if it's something that exists outside. Stuff that you just didn't expect or appreciate. And then, furthermore, the choice to be able to introduce that machine learning or AI model routine into there to even further kind of drift away from the actual ability to process in a deterministic way or behave in a deterministic way, really has to be taken seriously. And it's nice to be able to hear that there's really good considerations for that. So.
Justin, is there anything that you've seen in practice that you'd like to call out on that thread?
In practice of like introductions of AI in general, or in
Just
the case of deployed stuff?
Yeah, in the case of deployed stuff. I mean, we're working with a lot of folks who are doing this stuff in the field. Has there been any like interesting takeaways, things that didn't quite land well in production?
Yeah, there's I mean, we all have funny stories about situations where you expect something to work, and then the quirkiest situation, like stuff, ends up taking hold. I remember there was we had a hardware controller that was controlling like a connected PCIe cards too, that had issues where yeah, we were talking another day about something like this, where it was the chips were overheating, and it was just because the environment they would be put into was a warehouse that was like 100 and some odd degrees. Nobody selected parts to be able to operate in high temperature domains, and so they ended up finding solutions where they would actually put frosty ice packs underneath them for the day, you know. And it's like this is obviously the hardware fix while you have boards on hand. But that was one of them. And another one I always come back to, it's like we do have to prepare for so much of the unknown. In the case of embedded designs, that's why redundancy in computer systems and complexity and consensus came around, is just because situations where even something so much as the physics of our world and charged particles flying all around us for reasons, of us whizzing through space at tons at an insane speed, can flip bits in our systems and cause error to happen. And so it's like stuff like that that you just can't even predict, or you're not even prepared for, has to come about. What have you seen, Jeff? I mean, you've had
Yeah.
had
Oh
some
yeah.
quirky stuff.
I think a couple. I mean, yeah, I love everything you just said, because there are two that have come up for me that I think, really sort of like that last one especially, right? Like you can't, like the environment, right? Like weird stuff happening in the environment, electrons, you know, physics makes sense until you get really small, and then it just kind of stops working, right? Like electron tunneling and stuff is just, that I'll leave that to the physicists. But we had a client come to us. They were building submersibles, right? And when you think about like how do you debug a system, you want to talk about deploying machine learning, deploying vision models into these areas where you're using them in mission critical scenarios. But then what happens when something goes wrong? If the model or your algorithm can't explain itself and you can't kind of backtrack what's going on, it's really difficult to come up with fixes, right? And so we had this client, they were developing submersibles, and they were deploying and they were testing in a lab, everything was working great. And then they'd get out in the field and it would stop working. And sort of like really weird glitches, really strange errors. And what we were helping them debug, and what we found was that it was because it was getting slightly too cold, and so they weren't passing timing anymore on their FPGA, and they were starting to get like clock glitches. And it's one of those things that, like, when most people, I mean, not to get things too hot, right? But like thinking about like, oh, the physics of cooling something makes it more efficient, and so things operate a little more quickly, and so if you have a marginal timing path, something might fail, doesn't really cross your mind in the vast majority of systems, right? But when you're starting to look at deploying with an FPGA, and you're doing some machine learning acceleration on that FPGA, and then the model just starts spitting out garbage, that's really difficult, and so like how do you debug that? How do you deal with that? Well, you put it in a refrigerator while you debug, right? Which is, most developers don't have to like pick up their MacBook and go sit in the walk-in. But and to your point about like understanding the environment, understanding the world around you, and dealing with these fallback cases. Like it is a previous employer of mine. We built basically CNC machines, like 5-axis CNCs for duplicating house keys. And we made a choice, like there was a strategic choice made to really lean heavily on computer vision and machine learning on these robots, because all of our competitors sort of leaned very heavily. Like I think one of our competitors is actually like a pinball machine manufacturer, and they were like, hey, we're going to make key machines. So they were like these like beautiful, like super intricate mechanical machines. And we were like, yeah, we can do better with like whiz bang AI stuff. And what we found was that, deploying these models, like keys are actually a fantastically complicated concept. Like structurally they're very simple, right? It's like a milling line, and then you've got bits carved into it. But when you actually get out into the field, you find out that like locksmiths are also very clever. And so like, your quickset key that you've got, you can actually cut a quickset bitting pattern on an arrow key blank, and it'll fit in the lock and turn. But with, if you look at any one of those individual components by itself, you can't actually tell, is it a quickset? Is it an arrow? Like, I don't know what this is. But the machine learning model is like, hey man, it's quickset. Or, it's confident, just tells you, right? And so we have to start, we actually had to sort of work backwards, right? So we went machine learning first, and then actually had to like reverse engineer all of these different sort of mechanical traits out of keys, and then build sort of statistical models. So like when the machine learning gave a confidence interval that wasn't high enough, we then had to like fall back. And I think there's an interesting question there of like, should we have gone the other way? Should we have basically tried to do like sort of traditional computer vision measurement to try to like identify these things, and then apply machine learning on top to maybe either improve efficiency or like answer the questions we couldn't answer with sort of traditional methods? So I think there's, like, I think right now we're at this inflection point where like AI comes first, because it's I'm going to say cheap, easy to do. And then we're sort of finding the rough edges where it doesn't fit, and then having to like engineer the solution to how to answer the question after the fact. And right. And like when you think about from like an NRE perspective, again, is that the right way to go, right? Like you're sort of like trying to do the easy thing first and then having to build the wall after. Maybe you should have gone from the other direction. That's not to say I know any better. I mean, honestly, man, like Claude and ChatGPT are like miracles of engineering. It's incredible to me, right? So maybe I'm wrong. I'm just I'm turning into old man who yells at sky about AI, right?
Yeah, I think we'll like table a little bit of this for the last topic around like AI at the edge and safety, but it is very interesting to think about like the probabilistic situations for physical systems. And like so much of programming, like me growing up, I'm like I can write the thing and it's gonna be like 42 every time, and that's not necessarily the world that we're in anymore. I do want to do a quick detour. Like you guys do a lot of FPGA stuff. Like what brings you to that world? Like when do you need to go from microcontroller based applications to FPGA, and like how do you think about that?
Yeah. So it's with microcontrollers getting so fast and so good, and also starting to have really complex, sophisticated peripherals these days. The question of when to go to an FPGA is actually getting a lot harder to answer, right? Because like if you look at like a Raspberry Pi Pico, for like $1, right? Like 300K of RAM, you can slap like 5 megs of flash on the side of it. And it's also got this wonderful little finite state machine coprocessor. I think it's got like 8 of them, right? And you can actually do really sophisticated data capture and analysis activities with that block, right? And those are things that you might have years ago been like, I can't really do this in a microcontroller, right? So you would have maybe like brought some digital logic into bear. But like where we find use in FPGAs, so massively parallel data like data processing, right? So like, hey, we need to, we're trying to read an ADC at like 100 megahertz, and we're trying to run that 16 bits at 100 megahertz, and we want to I don't know, we're trying to like determine someone's pulse by like reading an ultrasound that's like pulsing through like their dialysis tube, right? Like, where something that you're processing significantly real thing, significantly more data than you could on a microcontroller, right? So when you need to do a lot in parallel, people talk about like the von Neumann bottleneck, right? Where basically it's, and you want to deploy an FPGA or maybe a custom ASIC anytime you hit a point where you simply can't process every event in parallel fast enough, right? Like you can try adding cores, you can resynthesize information, but at some point you're fetching an instruction and then you're dealing with the data, right? Even you start talking about like pipelining and stuff, sure, but like what if I need to like every single clock cycle do something useful with data and continue doing something useful with data, and sort of like move it through a sophisticated data processing pipeline. That's where you start thinking about FPGAs. Other places we think about using FPGAs, high-speed timing. So, we did some research with a lab several years ago now. I can't talk about it in significant depth. I think, I signed an NDA in blood at some point, but what I could say is basically like, you know what a pulse oximeter is, right? So it was basically remote pulse oximetry for the brain. So it like voxelized the brain, and you could look at blood density in the brain so that you could basically shoot photons through it. And then you basically, based on the wavelength of the received photon, you could sort of determine by like shooting a bunch of them in different directions, what regions of the brain were active. So it's like a really low resolution functional MRI, right? So when you're talking about capturing a photon and correlating it with an external event, right, you need to capture those things in parallel and then have multiple synchronous timers moving at exactly the same rate. And you need to be able to correlate these events within like nanoseconds. So you're not going to do that with a microcontroller, right? But you might.
Yeah, because photons, they're moving pretty slowly, right? Yeah.
Well, I mean, famously slow photons, right? Just waving their way in at a totally reasonable pace. But so that's a situation, right, where you're looking at it and going, okay, like what's the option here, right? Like maybe some sort of capture compare block and a really sophisticated timer system and a really nice microcontroller could maybe do that. but now scale it out. You're trying to do this
Yeah.
across multiple sensors, right? So it's when you, again, it's that parallelization piece, right? You simply can't do something in parallel with a microcontroller the way you can with an FPGA. Now, conversely, sometimes things are better suited to serialization, right? And like FPGAs, a lot of times when you get to like an extremely serial system, you end up deploying like a soft microcontroller core in an FPGA to sort of like give you that capability, right? Because like not everything can be easily expressed in pure digital logic. Sometimes it's a lot easier to, you're like, oh, I have this state machine, I'm like reading some level of instruction, and then at some point it's like I built a processor, and so you just slap a RISC-V in there and kind of call it a day.
And
That's like,
just really quick, I'm learning so much right now. And we don't see these things in the cloud as much, or is it just because the timing constraints, or like why is FPGA typically an edge product, or is there cloud applications too?
Yeah, there's I mean, FPGAs are deployed all over the place. We're actually, I mean, I would say traditionally FPGAs are data center products, right? They're used a lot in high-speed networking, sort of famously used a lot in like high-speed trading. Um, and it's because you need the autonomy to sort of like read in multiple parallel data streams, make decisions extraordinarily quickly, faster than you could sort of like fetch from memory and like go through your standard networking stack. And then you might employ like a TCP or maybe like a UDP stack directly in the fabric. And so like trade information comes in a binary format. They make decisions on it very, very quickly, and then fire the results back out over a network card. Used a lot in networking, especially like high-speed networking, like making routing decisions very quickly. You have like especially like IPv4, you have like a routing table. And so you can sort of like very quickly make packet switching decisions. We're only just now really starting to see them on the edge a lot more. Companies like Lattice and Efinix have developed extremely affordable, low power, low small size FPGAs for deployment in wearables, right? So like most of, I think like the original Pebble watch had a small like Lattice FPGA in it. Like most smart watches and things will have small FPGAs. And again, because they're trying to do sensor fusion, they're trying to do these things in like a very low power way. And capture a lot of parallel data and make decisions, and maybe not wake up their primary microcontroller, because it's going to be a little more power intensive.
It brings me great joy to think that FPGAs are the result of software engineers being tired of hardware engineers fixing hardware engineers' problems, and that they have the joy now to be able to participate in making their own problems.
Yes.
So similarly speaking, it's like, oh, we're engineers, we're infallible. Like all this stuff that I make definitely doesn't have bugs. So being that that's definitely a joke, and that hardware and software developers alike both make mistakes. How often do you find FPGAs being shipped with gateway products like microprocessors? I mean, I think about the Xilinx platform being like a package deal, such that you're updating this in the field. And how often do you find that on your route towards, let's say, crystallizing an FPGA design into an ASIC, do you see yourself doing updates to that software or to the fabric itself?
Yeah, great question. So I think that, to what degree do we see things being deployed in like gateway products? I mean, I think where I'm the most familiar with things we've done where people are shipping a box with an FPGA in it, cable set-top boxes, right? Often have FPGAs in them, right? And a lot of time, they're used for accelerating encryption. They're used for data stream decoding. They might make small changes to the protocol. They want to be able to update their firmware on their FPGA to maybe like provide some additional functionality to their customers without having to make a new custom ASIC. And so how often they're getting updated, I mean, it's sort of probably about the same cadence as any other software product, right? At whatever cadence you would normally release a firmware update, you're able to update your FPGAs. Now, in terms of how much do we see sort of changes on the way to making an ASIC? I mean, I don't often. It's somewhat rare that we see clients right now using FPGAs for the sort of like traditional process of like testing for like pre ASIC validation, right? Some do. What we're seeing a lot more is people deciding to go straight to ASIC, and maybe we use an FPGA to test small parts of the design, or we're just deploying an FPGA. And I think it's when you look at the cost as the cost of an FPGA comes down, and I mean now you can get an FPGA on par or cheaper than some microcontrollers, depending on the use case. whereas the cost of like a modern tape out, like a 7 nanometer tape out, it's like $25 million. So you could buy a lot of FPGAs for $25 million. And also that $25 million is one spin. That's one mask set. That's one set of wafers. So did you get it right? Maybe, maybe not. So maybe it's $50 million. Whereas if, you buy $25 million worth of FPGAs, like that might be every customer you ever need to serve and you can update it. Where you start to run into, needing an ASIC is really, you're trying to do more than FPGA fabric can really, either higher speeds, higher logic density. I mean, FPGAs are extremely massive now. I mean, like some of the Xilinx FPGAs, it's staggering how many transistor equivalent lookup tables they have. But those get very expensive. So when you're talking about like a modern ASIC, like you just can't fit that in an FPGA, like realistically, right? So it's kind of I'd say it's increasingly rare that a client is like deploying an FPGA and then they're like, we're going to switch over to an ASIC, because like you have to be pushing volume at that point. Like it has to be tens of thousands, millions of units before it really actually makes sense.
What do you think about the future of like the health and wearables markets and FPGA applications? Like that was a pretty cool. Like, do you think that there's gonna be a lot of attention there? I mean, I think that is where like any consumer product like is around like health and fitness are truly like durable categories, and people are always looking at that. And so potentially bringing this technology to consumers through that lens makes sense. But what are you saying? What do you think makes sense?
Yeah, I think, I would love to see, I mean, I'd always love to see more FPGAs deployed, right? Because that means more cool stuff for me to do. But I think in terms of like the health and wearables market, I think as we learn more about the human body, right? I think it's modern medicine is incredible and amazing, but I think we're still learning a lot. Human biology is very different. Like, me versus you, like, yeah, we're both humans. We're both white men working in tech. But I think that like biologically, the way our bodies function is like kind of follows a scaffold, but it's not exactly the same. So I think the more data we can give healthcare teams, the more data we can give ourselves about ourselves, the better. So like, deploying sophisticated sensor networks on body, I think, I mean, you have to question at what point you get, like the cool cyberpunk versus like cyberpunk dystopia, right? Like, I don't know if I really want like basement, wetware salesman installing stuff into my spine, but having like a ring that monitors my sleep, and tells me a lot, yeah, like oxygenation levels and stuff, I think is incredible, right? And I think that like FPG, when you start talking about like sophisticated sensor fusion and things, being able to deploy FPGAs in those markets and having smaller, lighter weight, lower power FPGAs is just gonna, it's gonna give us better and better data going forward. It's yeah, I mean, like some of the products we're working on right now, I mean, we're developing ASICs for it, but we need FPGAs to read the data out of those ASICs, right? So like, we're very quickly approaching a world in which, we're going to be able to, get extremely high resolution neurological data from animals and humans. I mean, Neuralink is currently doing this, although, you question the ethics of how they're sort of going about the installations and things. But I think, in 10, 15 years, once things are sort of hammered out, what if you could have have a wearable with an FPGA and like a custom ASIC in it that sort of tells you like, hey, like serotonin levels are dipping, right? Like, you've got, whether you have a neurological condition or maybe, you're having a bad reaction to like like an SSRI or something, right? So
Yeah.
I think there's like, it's going to be incredible what we see in the next 10, 15 years with sort of medical wearables.
Justin, I know that this is close to your heart. Anything you'd like to share on kind of wearables and neurotech?
I can't agree more. I think that there's so much more to be able to discover. I mean, even internally as well, like a neurological has always fascinated me, and those pathways. I think that there's a crossover between machine learning processing. You mentioned that you've been leveraging FPGAs to be able to accelerate some sort of AI routines. There's interesting areas in that domain as well, and yeah, I think as we move from FPGAs to like ASICs for like reasons of miniaturization or efficiencies or like scale, as you mentioned, as being a big factor as well, it's going to enable things to be able to go internal. Also, I think GI plays a big part of that. Um, Yeah, I just think this conversation just makes me want to go mess around with some FPGAs more, and I know that the software stack is like death by 1,000 paper cuts, but
It's so bad. Yeah, get downloading now if you have a slow internet connection.
How good are the LLM tools on your FPGA, your
So
VS Code extension?
so that's actually that, it's really funny. A lot of the discourse around LLMs is, about how they're going to take software jobs, or, junior developers are going away, which I think it's so silly. Like, who makes senior developers if you don't have any junior developers? It's just gonna be like a bunch of geriatric senior, old developers, and then like
Yeah,
a bunch of
we're all
robots.
COBOL programmers at this point then.
Oh man, my first job was porting Fortran, man. So I don't. But I oh god, you could actually make a very healthy living being a COBOL developer. Anyway, sorry, getting off topic. I it's actually the tool, LLMs are extraordinarily bad at digital design. And I think that, so any developers watching this, if you're looking for like a safe haven for at least a few more years from the AI future we're creating for ourselves, learn Verilog.
Yeah, well, I mean, auto routers in general, even for digital circuit designs, have been notoriously bad. And it's the same similar principles that I imagine to what you're doing with trying to be able to do routing and design for FPGAs.
I think part of the issue is that, like, a lot of these software tools, they build context based on all their, all the training data that they have, and the vast majority of training data they have is probably like JavaScript, Python, C++, sort of like
Yeah.
desktop oriented languages. And when you try to get it to spit out some Verilog, it understands what Verilog is, but it tries to do things in a very software focused way, and like it's just not how it works, right? Like, I mean, what I always tell people is, like, you think about traditional, like, software engineering, you sort of like execute top to bottom, right? You do an instruction, you just, next instruction. Verilog executes from left to right. So like the whole, like all of it, right? And so like LLMs get very confused about what exactly is happening, and they just produce like notoriously like terrible designs. Like we see it spit out like these like crazy like infinitely nested for loops and things. It's just like, no, don't do that. But
So
yeah, no, it's interesting stuff.
I want to get to the last topic, which is going to be pretty cool in comparison to what we hear a lot about AI safety right now. But around AI safety and physical systems, what does that mean to you guys?
Go ahead, Justin.
Well, I was curious in the tee up of this one as well, is to talk a little bit about supervised versus unsupervised learning, and through this lens to start, because we talked earlier about living under constraints and how introducing AI and machine learning models introduces a lack of them. And I kind of wanted to poke at a little bit of the differentiation between approaching building the data set, because even back then you mentioned that with the example of using machine learning and on a vision problem to cut keys. But the reality was that you trained a perfectly good model. It just didn't have it was just a reflection of the knowledge that even you had at the time when you trained it. And so, through that lens, there's some people would say that unsupervised learning has a greater capability of identifying knowledge pathways that the operator themselves, when defining the system, didn't have, which can be productive. But I would argue that in those cases, you're introducing more uncertainty, because there is that inherent lack of knowledge that the operator had. So I'd be curious in your thoughts on that, or.
So I'm reminded of this really great video series on YouTube of this person who, they train AIs to play video games, like various video games. Like they train them to bowl, they train them to play like putt golf. And there's the golf one is fantastic because it, by the end can like shoot, like hit the ball and do like a pretty good job. But the technique it develops, it's all like physics based. The technique it develops is to like jump up in the air parallel to the ground and swing the putter and hit the ball. And it does like a great job. The aim is fantastic, but it lands on its face every single time. And it's like, this would kill a person, right? And I think that, but that's what unsupervised learning gives you, right? It like optimizes for the target. But there's like, the world is more than just like a black and white target, right? It's like there's a lot of like externalization, like externalized things that you have to take into account. And I think that so when we talk about like a robot, so like one of our sister companies, Pickle Robot Company, they develop like logistics robots, right? So like basically going into like hot trucks in the middle of summer and like unpacking boxes, like very, totally like unconstrained problem. And the thing is, like, it is technically like a cobot, right? Like, like humans are in and around these spaces, right? Well, the
Mhm.
fastest way for a robot to pick a box might be fatal to a human, right? Like, it could elbow him right in the face, and so you do things like you put up light curtains, you put up no walk zones, and you try to make sure that humans can't be in the danger zone. But when you're training this robot, you have to take these things into consideration. So like supervised learning versus unsupervised learning, I think is just an issue of the domain. If you have like if you have safety critical systems, I think you have to put a human. We're still at a point where I think a human needs to be in the loop and needs to be making some decisions about these training sets. Um, and I think that like I think about self-driving cars like a lot. I live in an area where there aren't a lot of them currently, but um, you know, I think what it boils down to is like, you know, when you have a system that has things like safety implications, where does responsibility lie when something goes wrong? If it's unsupervised learning, you're essentially saying, I'm like, no one here is responsible for the outcome, right? The robot did it, the robot trained itself. And that's like from a liability standpoint, that's just not true, right? Like, and so I think that like if you're gonna put a product out that interacts with humans or interacts with the public, I think that like purely unsupervised learning, at the very least, you need to have guardrails put up that are outside the models to sort of like guide them. And this is a really active area of research right now, is like how do you detect when a model has been compromised or is going to do something dangerous and sort of blunt the effect?
Mhm.
Because yeah, it's not everything is beepers for dogs and like mushroom growing pods and whatever. Like sometimes it's robots, sometimes it's autonomous vehicles, sometimes it's drone like delivery drones, and these things have to they have to interact with the real world, and so
Uh,
the real world has has consequences.
I mean, this is the same conversation about agents, and Satya did that interview a couple weeks ago when they were talking about their quantum chip and really around like delegating authority to agents. And we're like so far from that still. And so we're going to have more things we have to process and review. I mean, like the world is just one giant, fatiguing pull request at this point. Like you just have to like, like
Oh,
300 pages of stuff I need to approve in the morning because I'm not actually allowing my agent to do bank transactions or
mhm.
like actually send an email to that client.
Do
Even
you think that there's a place for in this, with all of these kinds of outcomes that can come from like an agent operating on your behalf or a machine learning model operating from an unsupervised training set, that we might see a great utility for digital ledger technologies as a means of appropriating quality audit trail? And we were talking about smearing massive complexity with massive complexity. But
solve
maybe
AI by
one
just putting
hand
it on
feeds the
the
other.
blockchain.
Yeah.
oh yeah, and then we can use FPGAs to accelerate the transactions.
Yeah. Here we go.
Let's
Startup. Let's
new
go.
startup. Yeah, let's get it, guys. uh I think yeah, things like provable models and things like whether it's a blockchain or just like a like a what's the word I'm looking for here, um like a chain of trust, right, of like where the model came from, how it was trained. I think that's an important like unsolved problem right now. Like we don't.
Starting with a chain of trust is certainly a great place to
You're
begin,
right.
right? Yeah.
But I mean like right now, I mean it's tough to even say like what's like, are there even any standards, right, for like what defines like model safety right now? And I
Mhm.
don't know that there are. Like we're kind of in like this wild, like very interesting to watch, but like also a little bit scary Wild West period where we have a lot of development happening, right? And like the development that's happening is sort of accelerating next generation development. So we're sort of outpacing our ability to, I'm not saying I want like heavy-handed regulation on all this stuff, but I guess what I'm saying is like we're not really, we're not necessarily stopping to ask if we should, right?
Mhm.
And I don't know, I mean, I don't know if it's real or not, right? But I'm sure you guys have seen the meme job posting about like, OpenAI wanted like AI wrangler like to sit next to the server with a shotgun. you know, and like, you know, are we doing enough of that? I don't know. And I think that even if we were, how do you prove it? You know, especially as, you know, and again, it's like, it's not a bad thing, but like hardware is becoming more accessible. Like the world's ability to, you know, my ability to buy like what would have passed as like a supercomputer 15 years ago, like the maybe, you know, like I think one of the AI, like the training rigs we built at Kimi was like, I mean, it was a couple of really nice NVIDIA Titans. And I think our machine learning guy was like, yeah, like if this computer had existed 10 years ago, it would have been like top 15 fastest, you know, like most flops like in the world, right? And it was just like kind of like a mid-range AI training computer at that point, right? And so I think that like as we democratize access to this technology, which I think is a good thing, it sort of just enables everyone to build and train these sorts of models. So like what, you know, what happens when, you know, the technology is moving so fast that we like can't rein it back in? And I don't know the answer to that. That's I'll leave that one for the tech philosophers.
Well, I think we need to leave this conversation at this moment. It's a really good final point. Thank you everybody for coming today. I hope you all enjoyed it. I very much enjoyed this conversation. It's been a lot of fun getting to go deep with you, Jeff and Justin. Please stay tuned for our next webinar. We'll do something towards the end of March, and I think it'll be around security on hardware devices. But see you guys on the internet. Thank you.
All right. Thanks so much,
Thanks,
guys.
Jeff.
Really
Thanks,
enjoyed it.
everyone.
Yeah, appreciate it.